Tonight, we are going to drift slowly toward one of the strangest ideas in all of physics, an idea so quiet and so unsettled that even the people who study it for a living still cannot agree on whether it is real. Before we go any further, if you want a brand new space topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. The idea we will sit with tonight is the white hole, the time-reversed twin of a black hole, a shape in the equations of physics that pours matter and light outward instead of swallowing them inward. Picture for a moment the universe as seen from very far away. Imagine drifting outward, slowly, past the bright disk of our galaxy, past the soft glow of nearby spiral arms, past the quiet veil of dust that hides the deeper sky. From this distance, our galaxy is just one calm pinwheel among many, and beyond it, in every direction, stretch billions more. Some shine in soft gold, some glow in pale blue, some are smudged and irregular, like spilled milk on black velvet. In this enormous dark stage, we have learned to recognize one kind of strange object very well. The black hole, a place where gravity has folded space so tightly that nothing, not even light, can climb back out. We have photographed the shadows of black holes now. We have heard the gentle ripples in space that two of them make when they meet. They have become, in a quiet way, familiar. But the equations that gave us black holes did something curious. They gave us a second answer at the same time. A mirror image, an object that behaves like a black hole running in reverse. Where a black hole pulls matter in and lets nothing out, this mirror object would push matter out and let nothing in. Where a black hole has a surface you can fall through but never return from, this mirror object would have a surface you can leave but never approach. It is, in the cold language of mathematics, a perfectly valid solution. A shape the universe is technically allowed to draw. We call it a white hole. And here is the heart of tonight's quiet mystery. We have never seen one, not clearly, not certainly, not even once. We do not know if a single white hole has ever existed in the entire history of the cosmos, or if every white hole that the equations permit is forbidden by some deeper law we have not yet found. The question hangs there, unresolved. Are white holes real objects waiting somewhere in the dark, slowly leaking matter into the universe? Or are they ghosts, permitted by the math, forever denied by nature? Some thinkers believe white holes must exist somewhere, simply because the laws of physics seem to allow them. The same equations that correctly describe black holes also describe these reverse twins. And the universe has a habit of using everything its laws permit. Others believe the opposite. They argue that white holes would be so unstable, so fragile, so at odds with the way heat and disorder move through time, that nature would never quite let one form. Both views are held by serious people. Neither has been settled. There is even a quiet suggestion, whispered in some corners of cosmology, that the Big Bang itself, the great soft beginning of everything we can see, might have been a white hole event of unimaginable size, a single outward pour of all matter, all light, all space and time. If that idea is right, then a white hole is not a rare exotic object hiding in some distant galaxy. It is the place we all came from. Other thinkers disagree and call this picture beautiful but unproven. The equations allow it. The evidence does not yet require it. So tonight we are going to wander gently through this open question. We will look at how the idea was born. We will look at why the math seems to insist on it, and why the universe seems reluctant to deliver one. We will visit the strange surface that nothing can enter. We will sit with the bright bursts of light in the sky that some have wondered about, and others have explained away, we will follow the soft thread of an unsolved problem through 24 quiet rooms of thought. You do not need to remember any of it. You do not need to understand every word. You only need to rest and to let the question drift above you like a slow cloud on a dark sky. Somewhere out there, perhaps, matter is arriving from nowhere, or perhaps it never will. Let us begin with the simplest picture we can draw. Imagine a black hole. You have probably seen one rendered in soft, glowing images. A dark sphere at the center, a bright ring of hot gas wrapping around it. A pull so strong that even light cannot escape once it crosses a certain invisible boundary. That boundary has a name. It is called the event horizon. Think of it as a one-way door. Things fall in, nothing comes out. Now picture that idea and gently turn it inside out. A white hole, in the simplest terms, would be the mirror image of a black hole. Instead of a one-way door that only lets things in, it would be a one-way door that only lets things out. Nothing could ever fall into it. Matter, light, energy, dust, gas, all of it would pour outward, away from the horizon, into the space around it. From the outside, a white hole would look like a fountain, a bright, glowing point in the dark, pushing things away rather than drawing them in. That is the picture. A black hole swallows, a white hole spills. The strange part is that no one has ever seen one. Not directly, not in a telescope, not in any survey of the night sky. White holes exist at the moment only on paper. They live inside the equations that describe gravity. And yet the math seems to insist they are possible. The same set of formulas that gives us black holes also gives us their reverse twins. If one is real, the other might be too. That is the open question that pulls this whole episode along. It helps to think about the size. A white hole, if it existed, would not need to be enormous. The math allows them at almost any scale. A tiny one might be no larger than an atom. A medium one might be the size of a city. A large one might span millions of miles, like the supermassive black holes we know sit at the hearts of galaxies. The horizon, the outer skin of the object, would be smooth, invisible, and silent. You could not approach it. The outward push of matter and radiation would hold you away, like trying to swim up a waterfall. The distance is another puzzle. Because we have never confirmed one, we cannot point to where any white hole might be. It could be next door, in cosmic terms, only a few light years away. It could be hidden inside a distant galaxy. It could be far beyond the edge of the observable universe. Or it could be that none of them exist at all, anywhere, ever. Each of these possibilities is on the table. The age is stranger still. Some theories suggest that white holes, if they form, would be extremely short-lived. They might flash into being and vanish almost at once, leaving only a brief pulse of light behind. Other theories suggest the opposite. They might be ancient. They might have been spilling matter outward since the earliest moments of the universe. The simplest, boldest version of this idea goes even further. Some researchers wonder whether the Big Bang itself, the great pouring out of everything from a single point, could be understood as a white hole event on the largest possible scale. That is one possibility. Others find it unconvincing. The argument is far from settled. The composition of a white hole, in the simplest terms, would be whatever matter happens to be coming out of it. Hot gas, plasma, streams of particles, light, perhaps even older material that had once fallen into a black hole somewhere else, now reappearing on this side. That last idea, that a white hole could be the exit of a black hole connected through some hidden tunnel. is one of the most beautiful pictures the math allows. It is also, as we will see in later sections, deeply uncertain. For now, hold the basic shape in your mind: a glow, a horizon, a direction, a thing that only releases, never receives. A point in space where matter seems to arrive from nowhere, with no past trail leading in, only a future trail leading out. The opposite of a drain, the opposite of a shadow, a bright fountain in the dark, allowed by the equations of gravity, and yet, so far, unseen. That is what a white hole might be. A simple idea, shaped by symmetry, sitting just at the edge of what physics permits. Whether nature has actually built one anywhere in the vast and quiet universe is the question we will sit with tonight. The answer remains open. The picture, for now, is only a picture. The story of the white hole does not begin in a telescope. It begins on paper, in the quiet scratch of a pencil. In the year 1915, a young man named Carl Schwarzschild sat in a field hospital during the First Great War, working through the new equations that Albert Einstein had just published. Einstein had given the world a fresh way to think about gravity. Gravity was no longer a force pulling between objects. It was the bending of space and time around mass, like the gentle dip a heavy stone makes on a stretched sheet. Schwarzschild took those equations and asked a simple question: what would the bending of space look like around a single, perfect, round mass, sitting alone in empty space? He solved it within weeks. His solution was elegant, clean, and complete. It described how light would curve near a star, how clocks would slow near a heavy body, and how, if a mass was squeezed small enough, space itself would close around it, like a drawn purse. That closed pocket of space is what we now call a black hole. But the equations did something strange. They did not only describe one object, they described two. The mathematics of general relativity does not care which way time flows. The equations work just as well if you run the clock forward as they do if you run the clock backward. This is true of most of the deep laws of physics. They are written in a language that does not distinguish past from future. So, when Schwarzschild's solution gave us a region where matter falls in and never escapes, the same solution, read in the other time direction, gave us a region where matter rushes out and nothing can fall in, a mirror image. A second mouth. For decades, almost no one took the second mouth seriously. The black hole side of the solution was strange enough. The idea of running it backward felt like a curiosity, a quirk of the math, the kind of thing you mention in a footnote and move on. The equations allowed it. Nature surely did not. Then, in the 1960s, two physicists named Martin Kruskal and George Shekarus redrew Schwarzschild's solution in a new coordinate system. Their map of the full geometry revealed something remarkable. The complete extended Schwarzschild spacetime is not one region, but four. There is the outside universe we know. There is the black hole interior, where everything falls toward a central point. There is a second outside universe, separated from ours, and there is a fourth region, the time-reversed twin of the black hole, a region that pushes matter out instead of pulling it in. This fourth region is what the Russian cosmologist Igor Novikov named, in 1964, a white hole. The word stuck. It was a clean opposite. Black because nothing escapes, white because nothing can enter. The birth of the white hole, then, was not a discovery in the sky. It was a discovery on a page. The object was born from symmetry, from the quiet insistence of the equations that if one thing is allowed, its mirror must also be allowed. Many of the great predictions of physics have arrived this way. Antimatter was predicted before it was found. Gravitational waves were predicted decades before they were heard. The mathematics often runs ahead of the eye. The question is whether the white hole follows that same pattern. Does it wait somewhere out there for an instrument sensitive enough to catch it, or is it different? Is it one of those ghost solutions that the equations permit, but the universe refuses to build? There are reasons to think it might be the second kind, the second law of thermodynamics, the rule that disorder tends to increase, that broken cups do not reassemble themselves, seems to forbid the existence of a fully formed white hole sitting in space, waiting to spill matter outward. The arrow of time in the world we live in points one way. Stars burn down, heat spreads out, order decays into disorder. A white hole would seem to run the film backward, yet the equations do not know about that arrow. The equations are blind to it. And so, more than a century after Schwarzschild scribbled his solution by candlelight in a war hospital, we are still left with the same quiet puzzle. Two doors are drawn on the page. One of them we have seen. The other has never been opened. We do not know if it leads anywhere. We do not know. If anything stands behind it, the mathematics says it should be there. The sky has so far stayed silent, and that silence is part of what we will sit with tonight. Before we can wonder about a white hole, we have to wonder about what physics itself is made of. Not the stars and the dust, but the rules underneath them, the equations, the patterns, the quiet symmetries that hold the universe together like an invisible scaffolding. And when you look closely at those rules, something strange appears. Most of them do not care which way time flows. This is one of the deepest puzzles in all of science, and it sits right at the heart of our open question tonight. The laws that describe how particles move, how light travels, how gravity bends space, almost all of them work just as well backward as forward. If you filmed a single electron tracing a path through empty space, and then played the film in reverse, nothing in the basic equations would tell you which version was real. Both would be allowed. Both would be lawful. The universe, at its smallest level, seems to be written in a language that does not know the difference between past and future. This is called time reversal symmetry, and it is built into the very materials of physics, the equations of motion that Newton wrote down hundreds of years ago, the equations of light and magnetism, the equations of quantum mechanics, and importantly for our story, the equations of general relativity, the ones that describe black holes. All of them have this quiet, mirror-like quality. They are made of pieces that can be flipped, and yet, when we look at the world around us, we never see time run backward. Cups shatter on the floor, but pieces of glass never gather themselves up into a cup. Smoke rises from a fire, but it never gathers back into wood. Stars burn their hydrogen into helium, but helium does not reassemble into fresh fuel. The universe at our scale has a clear direction, an arrow pointing forward, even though the rules underneath seem to allow both directions equally. So where does the arrow come from? This is one of the oldest open questions in physics, and we still do not have a complete answer. One leading idea is that the arrow comes from something called entropy, a measure of disorder. The thought is that the early universe started in a very tidy, low disorder state, and everything since has been slowly spreading out, mixing up, becoming more tangled. The arrow of time, in this view, is really the arrow of growing messiness. But why the universe began so tidy in the first place? No one knows. This matters for white holes, because the same symmetry that allows time to run either way in the equations is exactly what suggests white holes could exist. If a black hole is a place where matter falls in and cannot escape, then running the film backward gives you a place where matter pours out and nothing can fall in. The math does not flinch at this. It simply allows it, the way it allows a ball to roll uphill if you reverse the film. The deeper materials of the cosmos echo this same strange double-sidedness. The iron in your blood was forged inside a dying star, then scattered outward in a great burst of light and shock. The water in every ocean may have ridden in on icy comets, ancient travelers from the outer dark. The carbon in every leaf, every bone, every grain of sand on every beach came from the slow nuclear cooking of stars that lived and died long before our sun was born. Everything we see is the leftover scatter of older, brighter things, and those scatterings, those explosions, those outpourings, all of them flow in one direction. Stars give, they do not take back. A supernova throws its layers into the dark, and the dark keeps them. We have never seen the reverse. A quiet patch of space suddenly gathering itself into a fresh, glowing star out of nothing. Yet the equations, if read literally, do not forbid it. They only seem to be ignored. So when researchers wonder whether a white hole could exist, they are really asking a much older question. They are asking whether the symmetry written into the fabric of physics is a real feature of the world, or only a feature of our descriptions of it. Some think the symmetry is genuine, and that somewhere, somehow, the universe must include objects that pour rather than swallow. Others suspect the symmetry is a trick of the math, beautiful on paper, but quietly forbidden by deeper rules we have not yet discovered. The answer, for now, sits unfinished. It rests inside the equations, waiting. The materials of physics permit two directions. The universe, so far, has shown us only one. Picture a black hole for a moment. Gravity there is so strong that nothing can climb away from it. Light falls in, gas falls in. Whole stars can be torn into ribbons and pulled across the edge. The forces all point one way. Everything flows inward, toward the center, like water spiraling into a drain that has no bottom. Now try to picture the opposite. Imagine a place where every one of those forces still exists, but the flow runs the other way. Light pours out, gas pours out, heat and pressure climb upward against gravity and somehow win. This is, in the simplest words, what a white hole would look like from the outside. The same equations that describe a black hole, run backward in time, describe something that pushes the universe away instead of drawing it in. Gravity is still the main character. A white hole, if one exists, would still bend space around itself in a deep, steep well. Yet the matter inside that well would not sit quietly. It would rise. It would climb out across the horizon and into the wider universe, as if the well itself were a fountain rather than a drain. From far away, an observer might see a bright object that simply will not let anything fall into it. Any infalling gas would be turned back, pushed outward by the steady flood of light and matter coming up from below. The pressure inside such an object is hard to even picture in an ordinary star. Pressure pushes outward and gravity pulls inward, and the two settle into a long, slow balance. In a white hole, the balance is broken in a strange direction. Whatever sits near the center is forced upward, not by a single explosion, but by the very shape of space-time around it. The geometry itself tilts outward. Time, in the math, leans the wrong way, and so matter follows that lean. The way a ball follows a slope, radiation plays a starring role in this picture. A white hole would shine, and shine brightly, because every photon trapped inside would have only one direction to travel. Outward, the light would not be a gentle glow. Some models suggest it would arrive as a sudden, fierce burst, lasting only a moment before the object emptied itself. Other models suggest a slower bleed, a steady leak of energy over a longer span. Which version is closer to truth, if either is, remains an open question. Magnetic fields might twist around such an object in unfamiliar ways. Around a black hole, in falling gas spirals into a flat disk, and magnetic lines wind tight as the gas approaches the edge. Around a white hole, the disk would have nowhere to form. Material would be flung off before it could settle. Some thinkers have wondered whether magnetic forces would shape the outflow into narrow jets, similar to the jets we see streaming from certain black holes, only running in the opposite sense. Others suspect the outflow would be wild and untidy, sprayed in every direction at once. The honest answer is that no one has watched one happen, so no one knows. Tidal forces add another layer of strangeness. Near a black hole, tidal forces stretch objects into long, thin threads as they fall. Near a white hole, those same forces would still exist, but their work would be done in reverse. Material rising out of the deep well would expand and cool as it climbed, the way steam expands as it leaves a kettle. By the time it reached the outside universe, it might look ordinary again. A puff of gas, a scatter of particles, nothing on its surface to whisper where it came from. Heat behaves oddly here too. In every system we know, heat flows from warm places to cool places, and disorder tends to grow. A white hole seems to push against that current. It would deliver order, in a sense, by sending out neatly arranged matter from a hidden interior. This tension with the second law of thermodynamics is one of the deepest reasons many researchers doubt white holes can truly exist in our universe. Others reply that the law might bend in extreme places, or that a white hole might be a brief, local exception rather than a lasting one. So the forces are familiar: gravity, pressure, radiation, magnetism, tides, heat. The cast of characters is the same, only their direction has changed, and that single change turns a quiet drain into a quiet fountain, and a known object into one we have never seen. Whether nature actually allows such a fountain to open anywhere in the cosmos is a question the next sections will keep gently turning over. Picture a black hole the size of our sun. If you could shrink the sun down to a sphere just under 4 miles across, you would have something close to the size of a stellar black hole. That is the width of a small town, a whole star, squeezed into a ball you could walk across in an hour. And around that little sphere sits the event horizon, the invisible edge that lets nothing back out once it has crossed in. Now imagine the opposite. A white hole of the same mass would have a surface of the same size, 4 miles wide, a quiet sphere hanging in space, glowing perhaps, or perhaps invisible until something poured out of it. The surface looks the same from a distance. The math gives it the same radius, but the rule that governs that surface is flipped. Nothing can cross inward matter. Light, even a single passing photon, would be turned away. Try to feel the strangeness of that, a surface the size of a small town that refuses every approach. Toss a pebble at it, and the pebble cannot land. Shine a flashlight at it, and the light cannot touch it. The closer anything gets, the more forcefully the geometry of space itself pushes it back out. It is not a wall in the usual sense. There is nothing solid there. The refusal is built into the shape of time near that place. For a more massive white hole, the numbers grow quickly. A white hole, with the mass of the giant at the center of our galaxy, would have a horizon about 17 times the width of our sun, place that object where our sun sits now, and its surface would still fit inside the orbit of Mercury, with room to spare. A region larger than several planets, yet still a single closed surface that nothing in the universe can enter. Scale it up further. Imagine a white hole holding the mass of 1 billion suns. Like the monsters that anchor distant galaxies, its horizon would stretch wider than our entire solar system. You could fit the orbit of Neptune inside it many times over, and still nothing could fall in. A bubble the size of a planetary system, and every grain of dust in the cosmos turned politely away at its edge. Now go the other direction. Shrink the idea down. A white hole with the mass of Earth would have a horizon less than an inch across, smaller than a marble, a tiny glowing pearl in the dark, holding the weight of an entire planet, and yet refusing to let a single atom approach. If one drifted past you in space, you might not notice it at all, except for whatever it happened to be spilling outward at that moment. The smallness is part of what makes the question so haunting. A white hole the size of a grape could weigh as much as the moon. A white hole the size of a sand grain could hold the mass of a mountain, and one no larger than a proton could still carry the mass of a small asteroid, slowly leaking that mass back into the universe as light and particles. Some researchers wonder whether tiny white holes like these could be drifting through space right now, too small and too quiet to find. The contrast with what we know is dizzying. A black hole the size of an atom would weigh as much as Mount Everest, and it would pull everything nearby into itself with overwhelming force. A white hole the size of an atom, by the same equations, would weigh the same and do the exact opposite. It would push everything away. Same mass, same radius, same warping of space, opposite relationship with time. The universe, in the math, seems perfectly willing to host both, and yet, when we look out at the sky, we see only the inward kind. We have mapped black holes ranging from a few times the mass of the sun to tens of billions of solar masses. We have seen the shadow of one. We have heard the ripples in space when two of them collide. The other kind, the outward kind, with the same range of possible sizes, has never shown itself. A mirror gallery of objects, predicted in every size from sand grain to solar system, and not one confirmed sighting. That is the scale of the puzzle. Not just one missing object, but an entire missing family, spanning every size the equations allow. Whether the universe quietly hides them, forbids them, or simply has not made any, remains an open question. For tonight, we can sit with the image of a small silent sphere, somewhere in the dark, gently refusing every visitor. Picture yourself somehow suspended in deep space, watching from a safe distance as a white hole hangs in the darkness before you. The first thing you would notice is the light, not a single point of light, but a steady outpouring, a soft and constant emergence of matter and radiation from a region that to all appearances should be empty. There is no flame, no roar, no visible source. The light simply begins to exist where it was not, and flows outward in every direction. This is, of course, a thought experiment. No one has ever stood near a white hole, because no one has ever found one. But the equations let us imagine the view, and the view is strange. If a black hole looks like a dark sphere pressed against the stars, a white hole would look like its photographic negative, a pale, luminous bubble. Some theorists picture it as a smooth pearl of light, faintly blue-shifted at its edges, where the outpouring slows. Others imagine it more like a fountain seen from far away, a steady spill of glowing material that fades as it spreads. The surface would not be solid, it would shimmer, the way a candle flame seems to have a skin without truly having one. And the color, the light leaving a white hole, would not be ordinary starlight. It would carry the fingerprints of wherever or whenever that matter came from. Some models suggest the emerging light would arrive heavily blue-shifted, pushed toward the violet end of the spectrum by the steep curve of space-time. Other models suggest the opposite, that the radiation would arrive stretched and reddened, like a long sigh after a long climb. Which picture is closer to the truth depends on assumptions we cannot yet test. This is where a quiet and beautiful idea enters the conversation. Some cosmologists have wondered whether the universe itself, in its earliest moment, behaved a little like a white hole. The Big Bang, after all, was a sudden appearance of matter and energy expanding outward from a region of extreme density. Light poured out, particles streamed away, nothing fell in. Seen through squinted eyes, the early universe and a white hole share a family resemblance. Some researchers have taken this seriously enough to ask whether our entire cosmos could be the interior view of a white hole sitting inside some larger reality. In that picture, what we call the beginning of time was simply the moment matter emerged through a one-way surface from somewhere else. The cosmic microwave background, that faint and even glow that fills the sky in every direction, would be the cooled echo of that emergence. The light we see when we look at the oldest sky would be, in a sense, the afterglow of a fountain that turned on long ago. It is a haunting thought. It is also far from proven. Most cosmologists treat the Big Bang and a white hole as separate ideas, and there are good reasons for caution. A white hole, as classical relativity describes it, would have a defined surface in space. The Big Bang did not happen at a point in space. It happened everywhere at once, in every direction. The geometries are not the same. The resemblance may be poetic rather than physical. Still, the question lingers. If you could float above a white hole and watch its surface, you might see something that looks oddly familiar. A faint, even glow, a texture of tiny ripples, like the gentle unevenness in the microwave background. A sense of beginning, frozen in place, replayed over and over. Some loop quantum gravity models add another layer to this picture. In those models, the surface of a white hole would not be smooth at all. At extremely small scales, it would seethe with quantum activity, a foam of emerging particles, each one stepping into existence and then drifting away. From far enough back, this foam would blur into the soft pearl we imagined earlier. Up close, the surface would look more like the boil of bubbles rising in still water. We do not know which of these pictures, if any, is correct. We do not know if any real white hole exists for us to see. The surface we have been describing is a surface no telescope has ever resolved. It lives in equations and in careful diagrams drawn on whiteboards, and in the patient imagination of the people who study them. For tonight, that is enough. A pale fountain in the dark, possibly real, possibly only permitted. A glow that might echo the first moment of everything, or might echo nothing at all. The question stays open, and the imagined surface keeps shining, quiet and steady in a corner of the mind. Now, we drift deeper into the strangest part of the idea. If a white hole exists, what would actually be happening beneath its surface? What kind of engine could pour matter and light outward forever, when every other object we know pulls things in. The deeper you go into this question, the more the picture begins to resemble a fountain hidden inside the fabric of space itself. Picture, for a moment, a slow rising plume of light at the heart of empty darkness. Not an explosion, not a star burning fuel, just a steady, gentle outpouring, as if some unseen spring were feeding the void with material. This is the image some thinkers reach for when they try to describe what lies inside a white hole. They call it, sometimes informally, a cosmic fountain. Matter rises, light rises, time itself seems to flow outward instead of inward. The mathematics behind this picture comes from the same equations that gave us black holes. When you write down the full solution for a non-rotating gravitational object, you find that the geometry has more than one chamber. There is the familiar pit, where things fall and never return. And there is a mirrored chamber, where things rise and never fall back in. The fountain idea simply takes that second chamber seriously, as if it were a real place rather than a mathematical curiosity. What sits at the bottom of such a fountain? Here the theories begin to split. One possibility is that the source is a singularity in reverse, a point of infinite density that, instead of swallowing everything, releases everything. Some researchers prefer this clean, symmetric picture because it mirrors the black hole exactly. The math is the same, only the direction of time is flipped. Another possibility is gentler. In certain models drawn from loop quantum gravity, a theory that tries to weave space-time out of tiny fundamental loops, the deep interior of a collapsing black hole never quite reaches a singularity. Instead, the falling matter compresses to an unimaginable density, slows, stops, and then begins to expand outward again. Seen from outside, this would look like a black hole that after an enormous span of time slowly transforms into a white hole. The fountain, in this view, is not a separate object at all. It is the second half of a long, quiet bounce. These two pictures lead to very different fountains. In the singularity model, the source is sharp, infinite, and forever mysterious. In the bounce model, the source is finite, smooth, and connected by a long tunnel of compressed time to a black hole that may have formed in some distant past. Both are allowed by current physics. Neither has been confirmed. The evidence remains incomplete, and the calculations grow harder the deeper one looks. There is a third quiet whisper in this conversation. Some researchers wonder whether the matter pouring out of a white hole has to come from anywhere at all. Perhaps the geometry simply allows new material to appear at the throat, drawn from no prior store. This would be deeply strange, because it would seem to violate the conservation laws we hold dear. The rules that say matter and energy must be accounted for. Most physicists find this idea unattractive, but the equations, taken at face value, do not strictly forbid it. The question of where the fountain's water comes from remains genuinely open. If you could somehow stand at a safe distance and watch such a fountain, what would you see? Probably not a fixed image at all. The light leaving the white hole would be heavily blue-shifted near the surface, and then red-shifted as it climbed away, giving the outflow a strange layered color. The matter, spilling outward, would carry with it temperatures and pressures from a region we have no way to measure directly. It would look, perhaps, like a slow firework that never quite finishes blooming, a pale, persistent glow against the dark. The depths of this idea are humbling. We are speaking, after all, about an object no one has ever observed. Every detail of its interior is reconstructed from equations, symmetries, and careful guesses about how nature behaves at extremes we cannot reach. The cosmic fountain may be entirely real, hidden in some quiet corner of the universe, or it may be a beautiful shadow cast by our mathematics, with no physical counterpart at all. What we can say, gently, is this: the equations do not forbid such fountains. They sketch them in surprising detail. Whether the universe chooses to draw them in matter and light, or leaves them as untouched lines on a page, is something we still cannot tell. The depths remain dark, and the fountain, if it exists, pours quietly on, far from any eye that has yet learned to look. Everything in the universe seems to move in cycles. Planets turn on their axes and trace long loops around their stars. Stars themselves are born from cold clouds, burn for ages, then collapse or scatter their outer skins back into the dark. Galaxies spin slowly, pulling their arms through the deep night over hundreds of millions of years. Even the universe as a whole may be breathing in some way we do not yet understand, expanding now, perhaps doing something different in the far future. Black holes fit neatly into this picture of cycles. They grow by feeding, they spin, they slowly leak a faint glow, if certain theories are right, and over unimaginable spans of time they may shrink and fade away. We can point at the sky and find them, weigh them, watch the gas circling their edges. They are part of the rhythm of the cosmos. White holes, if they exist, should also have rhythms. They should be born somehow, live for some span of time, and then end. Yet, here we run into one of the strangest parts of the mystery. We have never clearly seen one, not once, in all the patient watching we have done. Across every wavelength of light, no object in the sky has been confidently labeled a white hole. The cycle, if there is one, hides from us. There are several ideas about why this might be. One possibility is that white holes are simply unstable. Some calculations suggest that even a tiny amount of incoming matter or radiation would disturb a white hole so severely that it would collapse almost the moment it formed. In this view, the lifetime of a white hole would be far shorter than the blink of an eye. The universe is full of stray particles and gentle starlight. A white hole sitting in that soft rain of energy would not last. Its cycle would begin and end so quickly that we would have almost no chance of catching it. A second possibility is that white holes do exist, but only briefly and only in places we have not yet learned to look. Some researchers wonder whether short, sharp flashes of light in the sky, lasting only a fraction of a second, could be the gentle exhalations of tiny white holes finishing their lives. Fast radio bursts, those brief crackles of energy from far across the cosmos, have been raised as one speculative candidate. The evidence is far from settled. Most fast radio bursts seem better explained by spinning neutron stars or other known objects. Still, the idea sits there as a quiet possibility, waiting. A third idea is more patient. It says the cycle of a white hole is not short at all, but extraordinarily long. In some versions of loop quantum gravity, a black hole slowly transforms over a vast span of time. Matter falls in, gets squeezed, and then, through quantum effects we barely understand, the object bounces. It becomes a white hole and releases what it once swallowed. The catch is that, from the outside, this bounce might take billions or even trillions of years. The black holes we see today could be in the middle of that long passage. We would not notice the change because our lives are far too short to watch it unfold. Each of these ideas points to a different rhythm. One says the cycle is brutally fast. Another says it is hidden in faint bursts we have not yet decoded. The third says it is so slow that the entire history of human astronomy is only a single frozen frame of the motion. We have no clean way yet to choose between them. The silence of the sky is itself a clue. though a frustrating one. If white holes were common and long-lived, we should see strange fountains of matter scattered through the cosmos. We do not. If they were common and brief, we might still expect to detect their bright final flashes more clearly. Instead, we find a handful of puzzling signals and a great deal of quiet. So the cycle of the white hole, if there is one, remains unwritten. It may be a beat too fast for our instruments, or too slow for our lifetimes, or it may not exist at all. The equations keep whispering that such objects are allowed. The sky keeps refusing to confirm them. Somewhere between those two facts lies an answer we have not yet found. For now, the rhythm hides. The universe turns and breathes around us, full of motion we can measure. And somewhere in that motion, there may be a quieter cycle we have simply not learned to hear. It is a strange thing to rest with, this missing pulse, this absent tide. Nothing in the universe seems to stand entirely alone. Stars drift in clusters, galaxies gather in groups. Even the tiniest particles travel in pairs and chains. So when we picture a white hole sitting quietly in some far corner of space, it feels natural to ask what might be next to it. What kind of neighbors could such a strange object have? And could one of those neighbors be a black hole, joined to it by some hidden bridge between two mouths? This idea did not come from imagination alone. It came from the equations themselves. When physicists drew out the full geometry of a simple, non-spinning black hole, they noticed something curious. The math did not stop at the black hole. It seemed to continue, opening into other regions of space and time. One of those regions looked like the time reverse of the black hole. Another looked like a separate universe entirely. And linking these regions was a narrow throat in the geometry, a kind of tunnel that some scientists began to call a bridge. This bridge has a formal name. It is sometimes called an Einstein-Rosen bridge, after the two physicists who first described it in the 1930s. In its simplest form, it connects a black hole on one side to a white hole on the other. Matter, falling into the black hole mouth, would in principle travel through the throat and emerge from the white hole mouth on the far side. The two objects would be partners. One eats, the other gives back. It is a beautiful picture. It is also, almost certainly, not something nature actually builds. The mathematical bridge of the simplest solution turns out to be unstable. If you study the geometry carefully, the throat pinches shut, faster than anything could ever cross it. Even a beam of light, the fastest traveler in the universe, would not make it through before the tunnel closed. So whatever this bridge is, it is not a doorway you could walk through. It is more like a flicker in the equations, opening and shutting before anything can use it. That has not stopped researchers from wondering whether more complicated versions might survive. A spinning black hole, or one with electric charge, gives rise to a richer geometry. In those cases, the inner structure becomes layered and strange, with multiple horizons and regions that, on paper, seem to allow some kind of passage. Some theorists have asked whether a spinning black hole might connect, through its inner workings, to a white hole region in another part of space-time, or perhaps in another universe altogether. Others argue that the same instabilities return in disguise, and that any real matter falling in would tear the bridge apart long before it could be crossed. There is a softer version of this neighborhood idea, one that does not require travel at all in certain models of quantum gravity. A black hole and a white hole are not separate objects joined by a tunnel. They are the same object, seen at different stages of its long life. The black hole forms, compresses matter inward for an enormous span of time, and then, very slowly, transitions into a white hole that releases what it once held. In this picture, The bridge between two mouths is not a tunnel through space. It is a passage through time. The neighbor of a white hole, in this view, is its own earlier self. Other researchers prefer a stricter reading. They argue that white holes, if they exist, would be lonely objects with no black hole partner at all. They might be leftovers from the early universe, scattered like seeds across the cosmos, with no connection to any specific black hole anywhere. Under this view, the neighborhood of a white hole looks no different from any other patch of space. Just stars, gas, dust, and the slow drift of galaxies, with one quiet fountain in the middle, pouring out matter for reasons no one fully understands. We do not know which of these pictures, if any, matches reality. The bridge might be a real feature of nature, hidden inside every black hole, waiting for a future theory to reveal it. It might be a mathematical ghost, allowed by the equations, but never built by the universe. It might be a metaphor for something deeper that we have not yet learned to describe. Each possibility leaves the central question untouched. We still do not know whether white holes have neighbors of their own kind, or whether they stand alone in the dark, with only ordinary space around them, and only the faint, unproven promise of a tunnel that no one has ever seen. Picture a quiet patch of sky, somewhere between the stars. Nothing seems to be there. No glowing cloud, no distant sun, no whisper of dust. Then, without warning, light begins to pour from that empty place. Matter follows the light, streaming outward in a slow, bright spill, as if a hidden faucet has been turned on in the middle of nothing. This is the strangest image a white hole offers us. A point in space that holds no past we can trace, suddenly giving birth to things. The matter does not come from a star. It does not come from a cloud. It seems to arrive from nowhere we can point to. The extremes of this idea are hard to hold in the mind. A small white hole, only a few miles across, could in theory release as much energy in a single moment as the sun gives off across many lifetimes. The light would be brighter than a galaxy. The heat at its surface, if it has anything like a surface, might climb to numbers our instruments cannot measure cleanly. Some theoretical models suggest temperatures that would dwarf the cores of the hottest known stars by many orders. And yet in other models, the opposite is true. A white hole might be cold and quiet. It might leak its matter slowly across enormous stretches of time, so slowly that no telescope could ever catch the spill in a single glance. One idea says the outpouring is sudden and violent. Another idea says it is gentle and almost invisible. Both ideas come from the same equations. Both wait for evidence that has not arrived. The rarest version of this object, if it exists at all, might be the oldest thing in the sky. Some researchers wonder whether tiny white holes could be relics from the first moments after the Big Bang, drifting through the dark for nearly 14 billion years. They would be older than every galaxy, older than every atom of carbon, older than the first grain of dust that ever cooled. If even one survives, it would be a fossil from the universe's first breath. The fastest behaviors live in these models too. A. White holes ejected matter, in some scenarios, would race outward at speeds close to light itself. The particles would leave so quickly that anything wandering near the horizon would be pushed away before it could approach. Nothing falls in, nothing waits at the edge. The surface acts like a one-way wall, but the door opens outward, not inward. The coldest scenario is the strangest of all. Some loop quantum gravity models suggest that the white hole phase of a bounced black hole could be incredibly faint. The light it releases might be redshifted so deeply that its glow falls below the temperature of the cosmic background itself. A white hole, in this picture, would be colder than the empty space around it. It would hide in plain sight, leaking its slow contents into a universe that cannot tell the difference. The deepest extreme is the question of what comes out. If a white hole is the time-reversed twin of a black hole, then whatever fell into the black hole long ago could, in principle, emerge here. Stars, planets, gas, dust, light, all of it returned. But the order would be wrong. The matter would arrive scrambled, broken into the simplest pieces, with no memory of the shapes it once held. A planet that fell in would not come out as a planet. It would come out as a hot rain of particles, beautiful and unrecognizable. The highest puzzle sits above all of these. If a white hole truly spills matter into our universe, where did that matter live before it appeared? One theory says it crossed through a bridge from a black hole in a distant place, perhaps in another galaxy, perhaps in another universe entirely. Another theory says the matter was always there, frozen at the white hole's core, waiting for the right moment to be released. A third theory says the question itself is broken, and that our usual sense of cause and effect simply does not apply at these extremes. We have never seen any of this happen. No confirmed white hole has been found. The extremes we describe are extremes on paper, drawn from equations and patient guessing. The hottest, the coldest, the rarest, the fastest, the oldest. Every record belongs, for now, to a thing that may not exist, and still the math keeps the door open. Somewhere in the quiet sky, the equations whisper, matter might be arriving from nowhere we can name. The question of whether it really does remains, for tonight, beautifully unanswered. Settle in now, and let your thoughts drift toward the smaller details, the quiet textures of this puzzle. If a white hole did exist, even for a brief moment, what would its life look like from beginning to end? This is one of the gentler questions hidden inside the larger mystery, and it has its own quiet beauty. The lifetime of a white hole is not a settled number. It is a guess, wrapped in equations, a span of time that different theories paint in very different colors. Some calculations suggest that a white hole, if it ever formed, would not last long at all. The math hints that it could be unstable in the extreme. A single particle of light falling toward it might be enough to disturb the delicate balance, causing the object to collapse almost as soon as it appeared. In that view, a white hole would flicker into existence and vanish in a heartbeat, leaving behind only a soft puff of radiation and a small change in the surrounding space. Other models tell a slower story. In certain loop quantum gravity ideas, a black hole that has lived for billions of years might quietly turn itself inside out, becoming a white hole that releases its stored matter over an equally long stretch of time from the inside. This transformation would happen in an instant. From the outside, watching from a safe distance, you might see only the faintest brightening, spread thin across the ages of the cosmos. The same event, two clocks, two very different lifetimes. This is one of those small wonders that researchers find deeply lovely. Time inside a white hole, if such a thing exists, would not flow the way it does for us. It would stretch and compress depending on where you stood. A second near the horizon might equal 1,000,000 years far away. The shape of time itself bends around these objects in the math, and that bending changes what the word lifetime even means. Picture the surface again, that pale boundary nothing can cross from the outside. If a white hole were truly there, its glow might not be steady. It could pulse, it could shimmer. Some theoretical work suggests the spectrum of light pouring out would have specific patterns, soft fingerprints in the colors that telescopes might one day learn to recognize. No one has seen these fingerprints yet. But the search is gentle and patient, and the patterns themselves are the kind of detail that makes scientists smile when they sketch them on paper. There is another small wonder hidden in the lifetime question. If a white hole formed from the bounce of a black hole, its size when it appears would carry a memory of the black hole that came before. A small black hole would become a small, short-lived white hole, a giant one. The kind that sits at the heart of a galaxy would become something far longer lasting and far dimmer per moment, its outpouring spread across vast stretches of time. The biggest white holes in this picture would be the quietest. They would whisper their matter back into the universe, so slowly that no instrument we have built could tell them apart from the empty dark. This is a strange and tender thought. The loudest of these objects, if they exist, might be the smallest and the briefest. The grandest ones might be invisible by virtue of their patience. A galactic-scale white hole could be sitting somewhere in the sky right now, releasing a single photon every 1,000 years, and we would have no way to notice it among the endless background of starlight. Some researchers wonder whether the universe might be peppered with tiny, very old white holes, leftovers from the earliest moments after the Big Bang. These would be small enough to have nearly finished their lives by now, and their final puffs might appear as brief, gentle flashes scattered across the sky. Other thinkers find this idea unlikely, arguing that the conditions for forming such objects probably never existed, even in the wild first seconds of the cosmos. Both views remain on the table. Both are held softly, the way you might hold a question you cannot yet answer. There is no agreed lifetime for a white hole. There is no agreed brightness, no agreed signature, no agreed size. There are only the small details that the equations whisper, and the quiet hope that one of those whispers might match something the telescopes eventually find. For now, the lifetime of a bright mystery is itself a mystery. It could be a breath. It could be an age of the universe. It could be both at once, depending on where you stand and how patiently you watch the slow, dark sky above you. The story of how anyone began searching for white holes in the real sky starts, oddly enough, with a Cold War accident. In the late 1960s, the United States launched a fleet of satellites called Vela. Their job was not science. Their job was to watch for the gamma-ray flashes that would follow a secret nuclear test hidden somewhere on Earth or just above it. The satellites watched patiently, sweeping their detectors across the dark. They were looking for the signature of a bomb. What they found instead was something stranger. Beginning in 1967, the Vela satellites began catching short, intense bursts of gamma rays coming from somewhere far beyond the planet. The flashes did not come from any nuclear test. They did not come from the sun. They came from random directions in deep space, lasting sometimes a fraction of a second, sometimes a minute or two, then fading away. The discovery was kept quiet for years, while the military puzzled over it. When the results were finally published in 1973, astronomers around the world were left with a strange new mystery. Bright pulses of the highest energy light in the universe were arriving from nowhere they could explain. For decades, no one knew what these gamma-ray bursts were. Theories piled up in the journals like fallen leaves. Some thought the bursts came from collisions between neutron stars, the dense cinders left when massive stars die. Others suspected they came from the deaths of giant stars in distant galaxies. A few quieter voices wondered if they might be something far stranger. Among those quieter voices were theorists who had been working on the equations of general relativity for years, and who knew the equations allowed for objects nobody had ever seen. They wondered if these brief, brilliant flashes might be the long-predicted glow of a white hole finally announcing itself. The idea was not foolish. A white hole, if it existed, would by definition spill out light and matter without warning. It would have no history the outside universe could track. It would simply appear, pour energy into the sky, and then either fade or vanish. That description fit a gamma-ray burst rather well, at least at first glance. Several physicists in the 1970s and 1980s wrote careful papers exploring the possibility. They worked out what kinds of spectra a white hole might produce, how long the glow might last, and how its light might dim as the object aged. The trouble was that other explanations slowly began to fit even better. As telescopes improved, astronomers tracked gamma-ray bursts back to their host galaxies. They saw afterglows in visible light, in radio waves, in X-rays. They watched some bursts coincide with the death throes of huge, collapsing stars. They watched others ripple out from the merging of two neutron stars, an event later confirmed by the gentle stretching of gravitational waves. Piece by piece, the bursts were claimed by ordinary, if violent, processes. The white hole hypothesis quietly stepped back into the shadows. It never fully disappeared, though. A handful of bursts still resist easy classification. Some are too short, some too long, some too distant or too faint to fit the standard picture. And in recent years, a newer puzzle has taken the old one's place. Fast radio bursts. Discovered in 2007 in archival data from an Australian telescope, are millisecond flashes of radio light arriving from far across the universe. Their origins remain debated. Most researchers favor magnetars, the strongly magnetized remnants of dead stars, as the likely source. But a small number of theorists have proposed, gently and with full awareness of how speculative the idea is, that a few fast radio bursts might be the death rattle of small primordial black holes finally bouncing into their white hole phase. The suggestion is not mainstream. It is a quiet entry in the long ledger of guesses. What the history really shows is how science learns to live with mystery. The first gamma-ray bursts were misidentified as bombs. Then they were misidentified, perhaps, as white holes. Then they were partly explained and partly not. Each step taught astronomers to build better instruments, to argue more carefully, to hold a hypothesis loosely. No one has ever pointed a telescope at the sky and said with certainty, "There, that is a white hole." No one has ruled it out either. The search has shifted from gamma rays to radio waves, from the Vela satellites of half a century ago to the great radio dishes spread across the deserts of today. The question remains where it has always been, hanging quietly in the dark between what the equations allow and what the sky has been willing to show. Here is something that surprises almost everyone who first studies white holes. The equations of general relativity do not just allow these objects to exist. The equations seem to insist on them as a kind of mathematical mirror of every black hole. And yet, when physicists try to set up a white hole on paper, to give it a starting moment and let it evolve forward in time, something strange happens. The object does not want to stay still long enough to be born. This is the problem of stable beginnings. A black hole, once formed, sits quite comfortably in space-time. It can drift for billions of years, slowly feeding, slowly growing, perfectly stable in its silence. A white hole, by contrast, appears to be allergic to its own existence. The moment you try to place one in a real universe, with real radiation drifting past, the math suggests it would tear itself apart almost immediately. The reason is subtle. And it is one of those quiet details that even experienced researchers find a little uncanny. A white hole, by its nature, must repel everything. Light cannot fall into it, dust cannot settle on its surface. A stray photon from a distant star, drifting toward the horizon, would be pushed back outward with enormous force. But here is the strange part. As that photon climbs back out, the laws of gravity say it should gain energy in the process, not lose it, as light does when it climbs out of a deep gravitational well. Gain it, multiply this by every photon, every neutrino, every faint whisper of radiation that fills the universe. A white hole sitting in our cosmos would be bombarded constantly by gentle, harmless light. And it would convert each of those gentle arrivals into something far more energetic on the way out. Within a fraction of a second, by some calculations, the buildup of outgoing energy would overwhelm the structure entirely. The horizon would collapse. The white hole would, in effect, become a black hole, or simply cease to be a coherent object at all. This is sometimes called the instability problem, and it is one of the strongest arguments against white holes existing in our universe today. The math allows them. The math even seems to require them in certain idealized cases. But the moment you place one in a realistic setting, surrounded by the faint glow of distant galaxies and the cold hiss of background radiation, the object seems unable to persist. And yet, the story does not end there, which is part of what makes this such a quiet puzzle. Some researchers have pointed out that this instability calculation assumes the white hole has been sitting in our universe for a long time, soaking up incoming light. If a white hole were to appear suddenly, perhaps as the final stage of some other process, it might not have time to absorb enough radiation to destabilize before it finished whatever it was doing. A brief white hole, in other words, might be possible even if a long-lived one is not. Others have suggested that the instability problem itself depends on assumptions that may not hold in the real universe. The calculations often treat space as smooth and continuous all the way down. If space is instead grainy at the smallest scales, woven from tiny quantum threads, then the runaway energy buildup might never quite happen. The grain might soften the feedback, or it might make it worse. No one knows. There is also the question of where the outgoing matter would come from in the first place. A stable black hole has a clear origin story. A star collapses, gravity wins, the object forms. A white hole has no such tidy birth. To exist at all, it would need matter and light pouring outward from its horizon, seemingly from nothing, or from somewhere we cannot see. The equations do not specify where this material is supposed to be stored before it emerges. It simply appears, fully formed, traveling outward as if the universe had been holding its breath and finally let it out. This is the surprise that hides inside the surprise. The instability problem tells us that white holes cannot easily persist. But even before we worry about how they persist, we must ask how they begin. And the equations are oddly silent on that point. They describe the geometry beautifully. They describe the outflow precisely. They do not tell us where the contents of that outflow were waiting. Some researchers find this silence troubling, others find it suggestive, hinting that white holes are connected to something elsewhere, some other region of space-time we cannot yet see. For tonight, the question simply sits there, patient and unresolved, like a door whose hinges we have studied carefully without ever having seen the door open. The strangest part of the white hole question is that it does not sit alone. It touches almost every deep puzzle in modern physics, like a single thread that runs through a much larger weave. To wonder about white holes is to wonder about quantum mechanics, about thermodynamics, about the shape of space-time itself, and nowhere is that connection more delicate than at the edge, where the very small meets the very large. Black holes, as we understand them, are not silent. The physicist Stephen Hawking showed decades ago that the horizon of a black hole should glow faintly. This glow comes from the strange behavior of empty space at tiny scales. In quantum theory, the vacuum is never truly empty. Pairs of particles flicker in and out of being, borrowing energy for the briefest moment before vanishing again. Near the sharp edge of a black hole, one of those particles can fall in while the other escapes. Over vast stretches of time, this slow leak of energy could cause a black hole to shrink. If black holes evaporate this way, then their fate becomes a question no one has fully answered. What is left at the end? A speck of something, a puff of radiation, or perhaps, some researchers wonder, a doorway. The same equations that allow a horizon to shrink toward nothing also leave room for what comes after to look very different from what came before. One idea, gentle and unproven, is that the last moments of a black hole's life might resemble the first moments of a white hole's. The two might be linked quietly through quantum behavior we cannot yet observe. This is where loop quantum gravity enters the conversation. It is one of several attempts to stitch together the laws of the very small with the laws of the very large. In some versions of this theory, space itself is made of tiny woven loops, finite and discrete, rather than smooth and endless. When matter falls into a black hole, it cannot compress forever, because there is no smaller scale beneath the loops. Instead, the collapse slows, halts, and then reverses. The black hole bounces. From the outside, this bounce would take an enormous amount of time. From the inside, it might happen in an instant. And what emerges in this picture would not be a black hole at all. It would be a white hole, gently pouring its contents back into the universe. Other physicists are not convinced. They point out that the mathematics behind such a bounce is delicate. Small assumptions change the outcome. A different model of quantum gravity might predict no bounce at all, only a slow fade into radiation. The competing views agree on very little, and the experimental tests needed to choose between them lie far beyond anything we can build today. The bounce remains a beautiful possibility rather than a confirmed event. Still, the connections continue to spread outward. If quantum effects can turn a black hole into a white hole, then information may not be lost after all. The question of what happens to everything that falls past a horizon becomes a question of what eventually comes back out. Some thinkers suggest that the information is gently encoded in the radiation that leaks away, while others suspect it is stored until the very end, when the white hole stage releases it. No one yet knows which view, if either, is correct. There is also a quieter link, harder to picture, between white holes and the structure of time itself. Quantum mechanics, at its most basic level, does not strongly prefer one direction of time over another. Most of its equations work the same way forward or backward. The arrow of time we feel in our lives, the steady drift from order toward disorder, seems to come from the larger world rather than from the deep rules. White holes, if they exist, would be objects in which that arrow points the other way. They are quantum whispers, made enormous, written across the sky in matter and light, instead of across the page in symbols. So the white hole question does not stand apart from the rest of physics. It touches the slow evaporation of black holes, the woven fabric of space, the fate of information, the meaning of time. Each connection is fragile. Each rests on theories that have not yet been tested against the real universe. Yet, together they hint that the answer, when it comes, will not be a small one. It will reshape how we understand the smallest pieces of reality and the largest structures we can see. For now, the whispers remain just that, quiet suggestions at the edge of what we know, asking us to listen carefully and to keep wondering as the night settles in. Nothing in the cosmos sits perfectly still. Stars drift, galaxies wheel, even the empty space between them stretches a little wider each second, and ideas about white holes have drifted too, slowly across decades of quiet thought. One of the gentlest of these ideas is sometimes called the delayed birth hypothesis. It suggests that a white hole might not appear all at once, in some sudden burst. It might instead be the very, very late stage of a black hole that has lived a long and patient life. The idea begins with a simple observation. A black hole once formed does not last forever. It glows ever so faintly with a kind of slow heat first described by Stephen Hawking. Over enormous spans of time, that glow carries energy away. A black hole, the mass of the sun would take longer to fade than the present age of the universe. Many, many times over, but fade it might. And what happens at the very end of that long fading is one of the open questions this section sits with. In one family of theories, drawn from a field called loop quantum gravity, the inside of a black hole does not simply vanish. Instead, when the density inside reaches some limit that quantum effects will not allow to be crossed, the collapse halts. It rebounds. The matter that fell in long ago begins very slowly to move outward again. Seen from outside, the black hole would appear to live almost forever. Then, near the end of its life, its nature would quietly flip. It would become something that pushes outward rather than pulling inward. A white hole, a delayed birth. The appeal of this picture is that it does not need a white hole to appear out of nowhere. It does not ask the universe to produce a strange new object with no history. It only asks an old black hole to finish what it started. The matter that fell in is not destroyed. It is only paused, held in some compressed quantum state, waiting for its turn to come back out. Other researchers find this picture too tidy. They wonder whether the quantum bounce really works the way the equations suggest, or whether something else interrupts the process long before it can complete. The interior of a black hole is one of the least understood places allowed by physics. The math that describes a smooth bounce relies on assumptions that may not hold under the true crushing conditions inside, and there are competing theories in which the black hole simply evaporates away, leaving behind only a faint haze of radiation and an unsolved puzzle about where the original information went. There is also a question of timing. If white holes are the late, slow children of black holes, then most of them would not have been born yet. The universe is only about 13.8 billion years old. That is barely a moment compared to the time needed for a stellar black hole to finish evaporating. So in this picture, the sky would be almost empty of white holes today, because the universe has not waited long enough. Only very small, primordial black holes, formed perhaps in the first instance after the Big Bang, would have had time to bounce. Some researchers have wondered whether brief, unexplained flashes in the sky might be the final exhale of such tiny ancient objects. The evidence remains thin, the candidates are few, and other explanations fit just as well. There is a quieter version of the hypothesis that does not depend on quantum bounces at all. In this version, the universe simply allows certain regions of space-time to slowly change character over cosmic time, the way a frozen pond softens at its edges in spring. A region that was once a perfect inward trap might, after enough billions of years, lose that perfect grip. Matter held inside could begin to leak back out, slowly, gently, almost imperceptibly. Whether real physics permits this, no one yet knows. The equations are silent on the question. What is striking is how slowly all of this would unfold. A delayed birth, if it happens, is not a sudden event. It is a transformation stretched across more time than the cosmos has yet known. Black holes, in this view, are not endings. They are pauses, long, quiet pauses between two phases of the same object. The pull becomes a push. The dark becomes a glow. And the universe waits, patient as it ever was, for whatever comes next. We do not know if any black hole anywhere has yet reached that turning point. We may be living in a sky still waiting for its first white hole to be born. Light is how the universe tells its stories. Almost everything we know about distant things, we learn from the light they send us. The blue shimmer of a young star, the red glow of cooling hydrogen, the deep violet edge of a dying ember. Each color carries a message about what is happening far away, and inside that message is something even more delicate. Inside the light is information. When a star burns, the photons that escape it carry the fingerprints of its atoms. When a planet reflects sunlight, the bounced rays remember the chemistry of its clouds. Every photon is a tiny letter, sealed with the details of where it came from. Light, in a real sense, is the memory of the universe. And memory is exactly where the puzzle of white holes becomes most strange. For decades, physicists have wrestled with a quiet question about black holes. When something falls in, a book, a star, a single grain of dust, its information seems to vanish behind the horizon. The light it once carried can no longer escape. From the outside, all we see is a featureless surface, smooth and dark. Yet the laws of quantum physics say that information should never truly disappear. It can be scrambled, hidden, twisted into unreadable shapes, but it cannot be erased. This tension is called the information paradox, and it has haunted theoretical physics for 50 years. A white hole, if it existed, might offer one possible answer. Picture a black hole as a place where light and matter pour inward, and the universe seems to forget. Now picture its time-reverse twin pouring everything back out, photon by photon, particle by particle. In this view, the information was never lost. It was only stored, waiting, and then released somewhere else, in some other place or some other time. The light that once vanished returns as a flood of brightness. The memory comes home. It is a beautiful idea. It is also far from settled. One version of the picture suggests that a black hole and a white hole might be two ends of the same object, connected through a region we cannot see. What falls into one mouth comes out the other. The information rides the light, traveling along a hidden path, and emerges intact. Some researchers find this elegant, others find it deeply troubling, because the equations do not tell us where or when the other mouth would open. The exit could be in our own galaxy. It could be in a universe entirely unlike ours. It could be in a future so distant that no one would be left to witness the spill. A competing view says the information never needed a white hole to escape. In this picture, black holes slowly leak their contents through faint quantum radiation, a soft hiss of particles released over unimaginable spans of time. The light returns, but in disguise, scrambled so thoroughly that reading it would be like reconstructing a library from ash. The information is preserved, but the white hole is unnecessary. Both pictures aim at the same paradox. Both remain unproven. There is something poetic about imagining light as a thread that cannot be cut. Think of the soft golden glow of a candle, the way each photon flies outward, and carries with it the heat of the wax, the shape of the flame, the breath of the room. Now imagine that thread being pulled into darkness and pulled out again somewhere far away. Still warm, still remembering. If white holes exist, they may be the universe's way of refusing to forget, or they may be a story we tell because the alternative is uncomfortable. Nature has surprised us before by being stranger than our preferences. Perhaps information truly is lost, and the laws we trust need to be rewritten. Perhaps the light that falls into a black hole becomes something we do not yet have language for. The honest answer is that we do not know which picture is correct, or whether some third picture, not yet imagined, will turn out to be closer to the truth. What we do know is that light is patient. Photons that left distant galaxies billions of years ago are still arriving at our telescopes tonight, gentle and unhurried. If a white hole has ever bloomed somewhere in the observable sky, its light is on its way, or already here, hidden in a signal we have not yet learned to read. Somewhere in the soft static of the cosmos, the answer may already be waiting. We have only to listen carefully enough, for long enough, to hear what the light has been trying to say. Space, in the way we usually imagine it, makes no sound. There is no air to carry waves, no atmosphere to shiver against the eardrum. And yet the universe is not silent. It hums in other ways. Instruments pick up vibrations in plasma, ripples in magnetic fields, the slow swell of gravitational waves stretching the fabric of space itself. Scientists translate these signals into sound we can hear, and when they do, the cosmos begins to murmur. A black hole feeding on hot gas produces a deep, low-pressure wave in the cloud around it, a tone so deep it would take millions of years to complete a single beat. Pulsars tick like steady metronomes. The early universe, when its light was first set free, left behind a soft static we can still listen to today. If a white hole existed, what would its sound be? We cannot know, but the question is gentle to sit with. A black hole's voice, as we understand it, comes from matter falling in, swirling, heating, screaming in radio and X-ray as it crowds towards the horizon. A white hole running that story in reverse would be matter rushing out. The sound, if we could hear it, might be the opposite of a drain, a rising chord, a swell instead of a sink. That mirror image leads to one of the strangest ideas in modern physics. Some theorists wonder whether the universe itself has a mirror, not a copy floating beside us in space, but a twin reality running alongside our own, perhaps backward in time, perhaps with all its particles flipped. The idea is sometimes called the mirror universe hypothesis. In some versions, the Big Bang was not a single beginning, but a kind of two-sided event, with our cosmos expanding forward in time and another cosmos expanding backward, both born from the same quiet seed. If that picture were true, then white holes might be places where the mirror universe leaks into ours. Matter that fell into a black hole on the other side might pour out of a white hole on this side. The drain over there becomes the fountain over here. Other physicists are not convinced. They point out that the mirror universe idea is beautiful but very hard to test. It explains certain puzzles, such as why our universe seems to favor one direction of time by pushing the question into a place we cannot visit. Some researchers prefer a simpler view. They suggest that the apparent symmetry of the equations is just a feature of the mathematics, and that nature, for reasons we have not yet uncovered, chose only one of the two solutions to actually build. In that view, white holes and mirror universes are both ghosts. The math allows them, but the world does not. Still, the sound metaphor lingers. Think of a tuning fork struck once and held to the ear. It rings with a pure tone, and that tone is symmetric in time. Played forward or backward, it sounds the same. Many simple physical processes share this property. A pendulum swinging in a vacuum, two billiard balls colliding on a frictionless table. At the smallest scales, most of physics does not care which way the clock turns. The trouble begins when we gather many particles together. A cup of tea cools. A puff of smoke spreads. These large stories have a clear direction, and nobody fully understands why the small-scale symmetry breaks into a one-way river at the larger scale. The mirror universe idea is one attempt to balance the books. If our half of reality runs forward, perhaps the other half runs backward, and together they keep the deeper symmetry intact. A white hole in this picture would be a kind of acoustic seam between the two halves, a place where the song of one universe becomes audible in the other. We have no recording of such a seam. We have no confirmed signal that matches what a white hole's voice should be. The sky has been listened to in radio, in microwave, in gravitational waves, and so far it offers us only the familiar instruments of known physics. The cosmic background hiss, the chirps of merging black holes, the slow pulses of distant neutron stars. The mirror universe stays in the realm of careful speculation. Some find it elegant, a way to explain time's arrow without invoking anything supernatural. Others find it untestable and prefer to wait for evidence before granting it weight. The question remains open, and on a quiet night, with the stars overhead and the world dimming around you, it is enough to imagine that somewhere, in some form, the universe might be humming a note we have not yet learned how to hear. There is a quiet idea that the late Stephen Hawking offered, almost in passing in the 1970s. He wondered, on paper, whether a black hole and a white hole might be the same object seen in different ways. The thought was small and gentle, tucked inside a larger paper, but the math behind it had a strange kind of beauty, and it has stayed with physicists ever since. To understand why, picture the simplest black hole the equations allow. It has no spin, it has no charge, it carries only mass. The math that describes it is called the Schwarzschild solution, written down in 1916 by a soldier doing physics between battles. The full solution has just one variable that really matters. That variable is the mass. From that single number, the whole shape of the space-time falls out. The radius of the horizon is just 2 times the mass times the gravitational constant, divided by the speed of light squared. For a black hole, the mass of our sun, that radius is about 3 kilometers. For a black hole, the mass of the Earth, it would be smaller than a grape. The rule is elegant and clean. Double the mass, double the horizon. The numbers scale in a perfectly straight line. What Hawking and others noticed is that this same equation, with the same single number, describes a white hole just as well. You only have to flip the sign of time. The math does not blink. It treats both directions as equal partners. The horizon radius stays the same. The mass stays the same. Only the flow of events reverses. This is the quiet suggestion at the heart of the mystery. The equations of general relativity are time symmetric. They do not prefer past over future. If a black hole of 10 solar masses is allowed, then a white hole of 10 solar masses is allowed too. The arithmetic does not care which way the river of time is running. There is a deeper number hidden in this picture. It is called the surface gravity of the horizon. For a non-spinning black hole, that surface gravity is the speed of light to the 4th power, divided by 4 times the gravitational constant times the mass. From this single quantity, Hawking pulled something astonishing. He showed that the horizon must glow very faintly with a temperature. The colder the black hole, the larger it is. The smaller the black hole, the hotter it burns. For a black hole, the mass of our sun, at temperature is about 60 billionths of a degree above absolute zero. Almost nothing. Far colder than the deep space around it. For a black hole, the mass of a small mountain, the temperature would be hot enough to glow in gamma rays. The rule is again a clean inverse. Halve the mass, double the temperature. The math is simple, the meaning is vast. If a black hole has a temperature, it must also have an entropy, a measure of hidden disorder. Hawking and Jacob Bekenstein wrote down the formula. The entropy is 1/4 of the horizon area, measured in tiny squares called Planck areas. Each Planck area is about 10 to the minus 70 square meters. The number of these squares on the horizon of a stellar black hole is something close to 10 to the 77. It is a vast count, hidden inside a smooth, dark sphere. Here the equations grow quiet and strange. A white hole, run from the same math, would have the same entropy formula, the same area, the same temperature, but it would behave as if disorder were running backward, as if heat were flowing uphill, as if a shattered cup were lifting itself off the floor and rebuilding. The numbers fit. The physics is uneasy. Some researchers wonder whether this is a hint that we have not finished writing the laws. They suspect that a deeper theory, perhaps a theory of quantum gravity, will pick a direction in time and tell us why. Others wonder whether the symmetry is real, and whether somewhere in the universe the math is being honored in full. One view holds that white holes are forbidden by the very nature of heat. Another view holds that they are simply rare, or hidden, or waiting. What both views share is the elegance of the equation that started it all. A single number for mass, a single radius, a single temperature, a single quiet entropy. From these few ratios, an entire universe of possible objects unfolds, and tucked inside that unfolding, gentle as a footnote, is the suggestion that time itself might not be as one-sided as it feels. The math leaves the door open. Whether anything walks through it is still unknown. Imagine, for a moment, what it would take to actually see a white hole, not to prove it in math, but to catch one in the act, pouring matter into the night. The hunt is more delicate than it sounds. Astronomers do not have a clear picture of what such a thing would look like. They only have rough sketches drawn from theory, and those sketches do not all agree. So, the search becomes a kind of careful listening, scanning the sky for something that arrives without warning and leaves no trail behind. The first problem is knowing what to look for. A white hole would brighten suddenly, perhaps in a burst of light, perhaps in a slower glow. It would release material that seems to come from nowhere, with no star, no cloud, no obvious source behind it. That sounds dramatic, but the sky is full of bright flashes. Supernovas erupt, gamma-ray bursts flare. Magnetars send out short, sharp pulses. Each of these events looks, at first glance, like something appearing out of nothing. Telling a white hole apart from these familiar things is the hard part. Some researchers have suggested that fast radio bursts might be worth a careful second look. These bursts last only a few thousandths of a second. They come from far across the universe, and most of them have no known source. A handful of theorists have wondered whether a small white hole, finally letting go of its trapped matter, could produce a brief signal of that kind. Other researchers are skeptical. They point out that fast radio bursts likely come from neutron stars with powerful magnetic fields, and the data so far supports that view. The white hole idea remains a quiet possibility on the edge of the conversation, not a leading explanation. The second problem is that a white hole, if it exists at all, may be very unstable. Some calculations suggest it would unravel almost as soon as it formed. A single grain of falling matter, a single photon drifting toward its surface, might be enough to collapse it back into something more familiar. If that is true, then the window for spotting one would be tiny. The burst of light would be brief, and the object itself would be gone before any second telescope could turn to confirm it. The third problem is location. A white hole could appear anywhere. There is no known process that points to a particular star system or a particular patch of sky. The search has to cover everything, all at once, all the time. That is why the new generation of sky surveys matters so much to this question. Wide field telescopes now sweep the whole visible sky every few nights, watching for anything that changes. Radio arrays listen for fleeting bursts at many frequencies. Gamma ray satellites keep watch from orbit. If a white hole ever did flicker into view, the odds of catching it are slowly improving. Yet even with all this watching, nothing clearly matches the prediction. Every bright transient event so far has been tied, sooner or later, to a known kind of object, a dying star, a merging pair of dense remnants, a flare from a distant active galaxy. The absence of a clean signature is itself a kind of clue. It may mean white holes do not exist. It may mean they are extremely rare. It may mean we are looking in the wrong way, with the wrong instruments, expecting the wrong colors of light. The data is quiet, and quiet data is hard to interpret. The balance here is fragile in a different sense than a planet's atmosphere. It is a balance between theory and observation, between what the equations allow and what nature actually does. If even one event were confirmed as a white hole, the picture of the universe would shift in a deep way. The arrow of time would suddenly seem less absolute. The link between black holes and their possible time-reversed cousins would become something to study, not just imagine. If no such event is ever found, that absence will also teach us something. It will tell us that nature is more selective than the math, and that some doors the equations leave open are doors the universe keeps locked. For now, the searchers keep searching. They sit with their patient instruments, watching the sky for a flash that does not fit the catalogue. They do not expect to find one tonight, or this year, or perhaps in any year of their working lives. The hope is softer than that. It is the hope of any careful watcher that the universe might, one quiet evening, do something surprising, and that someone will be looking when it does. Of all the puzzles that surround the idea of a white hole, none cuts deeper than the puzzle of entropy. Entropy is just a word for how disorder grows in a system over time. A cup of hot tea cools, a sandcastle slumps back into the beach, a room left alone gathers dust. Everywhere we look, things drift from order toward disorder, and they do so in one direction only. This drift is so steady, so reliable, that physicists call it the arrow of time. It is the reason we remember the past and not the future. It is the reason eggs do not unbreak themselves on the kitchen floor. A white hole, if it existed, would seem to point that arrow the other way. Matter would arrive without a cause. Light would gather itself out of darkness. A cold cloud of gas would warm and brighten on its own. To an outside watcher, the scene would look like a film running in reverse. And this is where the trouble begins. The second law of thermodynamics, which says entropy in a closed system can only stay the same or increase, sits at the very heart of modern physics. A white hole, taken at face value, would seem to break this law in the gentlest and most flagrant way at once. Some thinkers have tried to soften this tension. One idea is that a white hole does not really run time backward at all. It only looks that way from the outside in. Inside its own frame, entropy might still climb in the usual direction, with the spilling matter carrying its own forward arrow that simply meets ours from the opposite shore. In this view, the white hole is less a reversal and more a strange handshake between two regions of time. The math allows this reading. Whether nature allows it is another question entirely. A competing view goes the other way. Some researchers wonder whether white holes are forbidden precisely because entropy forbids them. The universe, in this picture, is not just shaped by the equations of gravity, but also filtered by the slow, patient rule that disorder must grow. The equations permit white holes the way grammar permits a sentence that no one would ever say. They are allowed on paper and quietly excluded by the deeper logic of how time actually flows. There is a third possibility, stranger and more open. The very early universe was, by all measures, in a state of astonishingly low entropy. Things were smooth, hot, and tightly ordered. No one fully understands why. The fact that disorder has been growing ever since means it had to start from somewhere very tidy, and that tidiness is itself unexplained. Some cosmologists have noted that a white hole event, spilling a fresh and ordered cosmos into being, would match the low entropy beginning we seem to need. The Big Bang, in this gentle reading, might be the only white hole the universe ever produced, and we are still living inside its long, slow exhale. That idea remains speculative. Other researchers prefer explanations rooted in inflation, in quantum fluctuations, or in the shape of space-time at its earliest moments. The low entropy of the early universe is one of the deepest unsolved problems in physics, and white holes are only one of many guesses sitting in the room. What makes this section of the mystery so quietly thrilling is that it ties the smallest detail to the largest. The cooling of a cup of tea, the dimming of a star, the slow rusting of an iron ring on a forgotten shelf. All of these are pieces of the same arrow. A white hole would either bend that arrow, hide it, or reveal that it had a beginning we do not yet understand. There is no version of the answer that leaves the rest of physics untouched. For now, the question sits open in a way that is almost beautiful. We do not know if entropy strictly forbids white holes, or merely makes them rare, or quietly permits them under conditions we have not yet imagined. We do not know if the order we see around us flowed out of a single white spill long ago. We do not know if somewhere in a quiet pocket of the cosmos, a tiny reversal is happening at this very moment, too brief and too distant for any instrument to catch. The arrow of time is steady tonight. Your breath slows. The room cools by a fraction. Somewhere a star gives up a little of its heat to the dark between galaxies, and in the equations on a chalkboard in a building you will never visit, a small ghost remains, neither proven nor banished, waiting patiently for the universe to make up its mind. There is an old idea, almost as old as general relativity itself, that a black hole and a white hole might be two ends of the same thing. The black hole would be the entrance, the white hole would be the exit, and the strange narrow space between them would be a tunnel through the fabric of space and time. This tunnel has a name. It is called an Einstein-Rosen bridge, after the two scientists who first wrote down the math. Most people simply call it a wormhole. A wormhole, in its purest mathematical form, is a shortcut. It connects two distant places, or perhaps two distant times, through a throat in the geometry of space. One mouth pulls things in, the other mouth pushes things out. Looked at this way, a white hole is not a lonely object floating by itself. It is the far side of something else. The matter that vanishes here might be the matter that appears there. It is a beautiful picture. It is also, for now, only a picture. The equations allow it. The universe may not. The trouble, as always, is stability. The simplest wormhole solutions pinch shut almost the instant they form. The throat collapses faster than light can cross it. Anything trying to pass through would be crushed before it reached the other side. To hold a wormhole open, you would need something stranger than ordinary matter. You would need a kind of stuff with negative energy, something that pushes outward against gravity instead of pulling inward. Physicists call this exotic matter. Whether it exists in the real universe in any usable amount remains an open question. In 1,000,000 years, our telescopes will be far better than they are now. In 1,000,000,000 years, the sun will have swelled and swallowed the inner planets, and whatever civilization remains will look out at a sky already changing. New stars will have formed from the dust of older ones. New black holes will have grown from the cores of dead giants. If wormholes are real, some of them may have opened and closed in that long span of time. Most would be far too small to see, smaller than an atom, flickering in and out of existence at the quantum scale. A few, perhaps, might be larger. Whether any could be stable enough to last is one of the deepest unsolved puzzles in physics. There is another version of this idea, gentler and stranger. Some researchers wonder whether every black hole in our universe is paired with a white hole somewhere else. Not in our space, not in our time, but in another region of space-time entirely, perhaps in another universe, perhaps in our own universe far in the future. In this picture, the matter that falls into a black hole today is not destroyed. It is delayed. It waits, compressed and patient, until the geometry on the other side allows it to emerge. The emergence might take 1,000,000,000 years. It might take far longer than the current age of the universe. A competing view holds that no such pairing exists. Black holes in this view are one-way doors. What falls in is processed, scrambled, and eventually released as faint radiation over unimaginable spans of time. There is no twin throat. There is no other mouth. The matter does not travel anywhere. It simply changes form, slowly and quietly, over a span so long that the rest of the universe will have grown cold and dim before the process completes. Both pictures live inside the same equations. The equations do not yet tell us which one nature has chosen. Far in the future, when the last stars have burned out and the galaxies have drifted beyond each other's reach, black holes will remain. They will be among the longest-lived objects in the cosmos. If even one of them eventually unwinds itself into a white hole, the universe will witness, in its old age, the strangest event of all, a sudden bloom of matter and light where there had been only darkness, a delayed exhale, billions or trillions of years in the making. We do not know if this will happen. We do not know if it can happen. The mathematics permits it. The physics, as we currently understand it, neither confirms nor forbids it. The tunnel may be real, or it may be a shadow cast by our equations onto a universe that does not actually contain it. The twin throat may be waiting, somewhere we cannot see, or it may be a beautiful idea with no home in the real world. For now, we sit with the picture, two mouths, one throat, a long, quiet tunnel through the dark, and the patient, unanswered question of whether anything truly passes through. Step back now. as far as the mind can stretch, see the whole night sky at once, a great quiet bowl of light and shadow, holding everything we have ever known. Somewhere in that bowl, the question we have been sitting with might finally find an answer. Somewhere in the next decades, a new instrument might catch a flicker that no old instrument could see. The mystery of whether white holes exist is not a closed door. It is a door we are still building the key for. The telescopes already on the way are remarkable quiet machines. Some float in cold orbits far from Earth, gathering infrared light older than our planet. Some sit on mountaintops with mirrors as wide as small houses, drinking in faint photons from the edge of the visible universe. Each new generation sees a little deeper, a little sharper, a little further back in time, and every time we sharpen our vision, the universe shows us something we did not expect. If a white hole ever erupted in our galaxy, what would these instruments notice? Perhaps a sudden bright point where no star had been the night before. Perhaps a strange burst of radio waves with a shape that does not match any known source. Perhaps a faint glow with the spectrum of the early universe, appearing in a place where the early universe should be long gone. The signatures, if they exist, would be subtle. They would hide among the ordinary fireworks of dying stars and feeding black holes, easy to mistake for something more familiar. This is why the search is patient work. Some researchers comb through archives of old observations, looking for events that did not quite fit the usual explanations. Others build wide-field cameras that watch the entire sky each night, recording every brief flash for later study. The hope is modest. We are not expecting to see a white hole tomorrow. We are hoping that, if one is hiding in the data, we will not throw it away by accident. And yet many thoughtful researchers suspect we will never find one at all. They argue that white holes are mathematical ghosts, allowed by the equations but forbidden by the way the universe actually behaves. Time, in their view, has chosen its direction, and matter falls inward, and entropy climbs, and that is the end of the story. The next telescopes, they would say, will reveal only deeper black holes, only stranger galaxies, only older light, no fountain, no reversed arrow, just the same slow forward flow we have always known. Both views deserve our quiet attention tonight. Both might be partly right. Step back further still. Think about where the atoms in your hand came from. The iron in your blood was forged inside a massive star that lived and died long before the sun was born. The calcium in your bones was scattered by a supernova that lit up some ancient corner of the galaxy. The oxygen in your lungs drifted for billions of years through cold gas clouds before settling here. You are not separate from the cosmos you are wondering about. You are a small, warm arrangement of its older pieces, asking questions about its larger shape. In that sense, the puzzle of white holes is not a distant abstraction. It is part of the same long story that built you. If matter can only fall and never return, then the universe is a one-way river, and we are passengers on a current that does not flow back. If matter can sometimes return, even rarely, even strangely, then the river is stranger than it looks, and we are part of that strangeness too. Either answer changes the shape of the story we belong to. Either answer is worth carrying gently into sleep. The next telescopes will not solve everything. They will find new mysteries faster than they resolve old ones. That is the quiet rhythm of this work. Each generation hands the unanswered questions to the next, a little sharper, a little better defined, with a few more clues attached. Someone listening to a sleep documentary 100 years from now may know things we cannot guess. They may also have inherited puzzles we have not yet thought to ask, For tonight, the sky above you is the same sky that has held this question for as long as anyone has looked up. The stars are not in a hurry. The galaxies are not in a hurry. The slow turning of the cosmos is patient with us and asks only that we keep wondering. The answer, if it comes, will come gently in the soft light of an instrument we have not yet built, pointed at a patch of darkness no one has yet thought to study. Until then, the question stays open and the night stays kind. We have walked a long way together tonight, through equations and horizons and quiet questions that no one has yet answered. Now it is time to let the thinking slow. The white hole, if it exists at all, will not be solved this evening. It will still be there in the morning, tucked into the seams of general relativity, waiting patiently for someone, somewhere, to find a way to listen for it. Imagine, for a moment, a small blue world turning slowly in the dark. Its oceans catch the soft light of a single moon. The clouds drift in long ribbons across the dayside, and on the night side faint lamps glow in scattered patterns where people are sleeping. The planet does not hurry. It turns at its own steady pace, as it has for billions of years, carried in a long, slow circle around its star. That star is one of many beyond it. The galaxy turns too, a wide pinwheel of warm light, taking hundreds of millions of years to complete a single rotation. Inside that pinwheel, somewhere, a black hole may be quietly feeding. Somewhere else, perhaps, a white hole may be quietly waiting, hidden in a way we have not yet learned to see. The two ideas sit beside each other in the equations like a pair of doors, one closing, one opening, and we still do not know if both of them are real. There is something gentle about not knowing. The mystery does not press on you. It does not demand an answer tonight. It simply rests there, as old as the first moment of the universe, as patient as the slow drift of galaxies through the dark. You are allowed to wonder about it without solving it. That is what wondering is for. If white holes exist, they may be rare beyond imagining, scattered so thinly across the cosmos that we have simply not looked in the right place yet. They may be brief, flashing into being and vanishing again before any telescope can turn. They may be hiding inside the hearts of objects we already know, wearing other names, or they may not exist at all, and the symmetry in the equations may be a beautiful idea that nature, for reasons of its own, has chosen never to use. Any of these answers would be remarkable. The universe is allowed to be stranger than we expected, and it is also allowed to be simpler. Both outcomes carry their own quiet wonder. For now, picture the night sky above that small blue world. The stars are steady. The Milky Way arches across the dark like a soft river of light. Somewhere along that river, a black hole bends the path of a distant beam, and the beam goes on its way, only slightly changed. Somewhere else a galaxy is being born. Somewhere else still. One is fading. The whole great machine turns gently, without urgency, without alarm. You are very small inside all of this. So am I. So is everyone who has ever looked up and tried to understand. And yet the smallness is not lonely. It is a kind of belonging. The atoms in your hands were made in stars that died long before the earth had a name. The light reaching your eyes tonight, if you stepped outside, would be older than your grandparents, older than your country, older in some cases than our entire species. You are made of the universe, watching itself, asking quiet questions in the dark. The white hole may be one of those questions that we carry for a long time. Maybe a future telescope will catch a strange spill of matter that fits no other model. Maybe a new equation will rule the idea out, entirely. Maybe the answer will arrive in a way no one has yet imagined, from a direction no one is currently looking. We may know more in our lifetimes, we may not. Either way, the wondering itself is a gift. Let your breathing slow, let your shoulders soften. The cosmos is vast and gentle, and it does not need you to solve it tonight. It only asks that you rest here under the quiet light of stars whose names you do not need to know. The galaxies will keep turning, the equations will keep waiting, the mystery will keep its shape until the next curious mind comes along to hold it for a while. For tonight, it is enough to have looked, it is enough to have wondered, it is enough to lie still in a small warm room while the universe goes on being beautiful and strange and not yet fully understood. Subscribe for a brand new space topic every night. One tap and something incredible is waiting for you tomorrow. Sweet dreams.